then you can ask about the change in the area in going from one to the other. Yeah, I'm almost certain I'm doing something terribly, terribly wrong, and I'm overlooking something nice. So a scalar influences how the rows of the matrix. So the rows of the matrix don't change in shape. So it's not that the rows change in shape. It's like the picture you want to have in your head is like let's just be very, very concrete. Like, let's imagine that we have a square, the unit square, the square in the plane whose vertices are this, that, and that, right? Then we can apply, so this is R2 here. We can apply this, let's say we have a 2 by 2 matrix, A. We can apply this 2 by 2 matrix to every single vector in this plane, and we can imagine that what it spits out is again an element of R2. Okay. Is this the type of picture that you've seen before in your life? Like, if you have a vector, I hope you're used to this. Like, if you have a vector in the plane and its coordinates are v1 and v2, right? Then what you can do is look at the image of this vector under the matrix A, and the way that you obtain that is just to do A times v1 v2. Is this familiar at all? And this is going to be some other vector possibly, right? In the plane. Oh, there we go. I took linear algebra, but I forgot a bunch of stuff. I'm trying to relearn some of the stuff so I can create some project. Okay. Yeah. So remember 2 by 2 matrices, for example, or a matrix have 4 entries. A 2 by 2 matrix, for example, has 4 entries. I'm not explaining myself very well. I can feel it. Fuck me. Yeah, you're right. Let me fix that for you. How do I do that? Sorry, I'm still learning all this stuff. Yeah. OBS. Hello, OBS. Do that. Yeah. And then we can multiply this matrix by the vector v1, v2. And we get out, if we do that, a11, v1 plus a12, v2 and a21, v1 plus a22, v2, right? This here we can interpret as an element of R2. Similarly, this is an element of R2. This thing here is our matrix A. This is a vector V. And this thing right here is the product of A with V. Is that clear? Sure. R2 is the set. It's like the set of vectors in the plane. So like it's, the set of vectors of the form v1, v2, where v1 and v2 are real numbers. So you should view this. You visualize this thing. Visualized as a plane, right? So like R2 is just the plane. Sometimes it's often drawn with like axes like this, the XY plane. These are really synonyms. And what a matrix does is, you can view it as a function which eats a vector in R2 and spits out another vector in R2. And the way that happens is through matrix multiplication. So we have here A, a 2 by 2 matrix, V, a vector in R2, hence a 2 tall vector, like this, a 2 by 1 matrix, if you like. And when you multiply a 2 by 2 by a 2 by 1, you get a 2 by 1. And it happens to be this complicated looking thing here. No, this vector is not the determinant. Sorry. But I'm trying to give you an interpretation of the determinant. So the point is that if you think about this square right here, okay, in R2, then this square can get mapped by this function to a new square over here, or a new, rather, parallelogram. It might look something like this. I don't know. It could be mapped to something that looks like this. I don't know. Matrices are complicated. They can do all sorts of things. But what I'm trying to say is that like this black square will get mapped to that red parallelogram. Then what you can do is ask about the area, the relationship between the area of the red thing and the area of the black thing. And the determinant tells you a constant of proportionality. So the area of the black square will turn out to be equal to the determinant of A times the area of the red square. And there's some absolute value bars here involved, I'm sure. I think it's something more like this. So that's what the determinant does. But as Olha has said, you can use them for a lot of different things. I think from a mathematical point of view, they in a very deep way, actually, this area interpretation is really kind of the powerful one, but that takes a lot to explain. It's the thing which dominates. But one other interpretation or one other use of determinants that's very valuable for mathematicians is that when the determinant of a matrix is non-zero, that tells you that the matrix is non-singular. And that is a very powerful statement in and of itself. I don't know if that word non-singular means anything to you. The other interesting part, just for the math nerds out there, is that the determinant is a homomorphism. Well, it's at least a homomorphism. These are complicated words, but it's a homomorphism from if you are looking at, let's say, GL and K, where K is a field, it's a homomorphism from GL and K to K. Okay, yeah, if there is something that you want to know about the determinant, you can try to explain. And if you're confused, I don't know. If there is any other math questions out there, please let me know. What about eigenvalues and eigenvectors? So eigenvalues and eigenvectors are things that you associate with square matrices. And like one way of thinking about what they do, so an eigenvector, I'll just say it and then I can try to explain it. An eigenvector is a vector which is left invariant up to scale by a matrix. So what in the world does that mean? Does it mean anything to ask if the field is C? Then what does a complex determinant mean? Oh, you mean like the geometric interpretation doesn't feel like it holds anymore? Oh, shoot. The thing just did its thing. So wait, hold on. Just give me one moment. I need to see what happened here. Oh, shoot. No. No. Oh, no. Is some ruined? Wait, what? How? Okay, something is broken. Does it mean to ask if the field is C, then what does a complex determinant mean? I think I'm a little bit less sure about how to answer that question. It's a great question. I'd like to know the answer myself. I am less sure about how to answer it. But what is true is it's still the fact that if you have a square matrix whose complex determinant is non-zero, then that's a non-singular complex matrix, which is of interest in and of itself. But it is true that as I suspect the interpretation of the determinant as being representing the proportionality change in let's say the volumes of stuff, that no longer holds, right? Yeah. Or rather, it's a little bit weird to think about like the volume changing by a factor of 3 minus 4i. Yeah, 3 minus 4i. There was another question. Yeah, what are eigenvectors and eigenvalues? Sorry, I got sidetracked. Yeah, so if you have a non-zero vector v, this is an eigenvalue, or an eigenvector with eigenvalue lambda if, an eigenvector of A, my bad. So you have a matrix. Then it's an eigenvalue if the following equation holds, and then we're going to interpret this equation. If AV is equal to lambda V. Okay. So what that means is that when you hit V by the matrix A, which is just like applying a linear transformation to that vector V, okay, the effect of applying that function to the vector, the effect is merely to scale the vector. This